next speaker is Professor Chao-Tsung, Huang. He's a professor at our National Tsinghua University as well as Professor Lin. So his specialty is in computational photography, solid-state circuits, and computing architecture, and has recently done a lot of, a series of great work on light field systems, and worked a lot on developing efficient VLSI architecture for these popular deep learning models. So, right, sorry, are you okay? Yeah. So let's welcome Professor Huang.
Thank the introduction from the Professor Huang. I'm Chao-Tsung Huang. I'm glad to share our recent work on bandwidth and energy efficient CINE acceleration for next generation cameras and displays. And this is my outline. I will talk about first the opportunities and challenges of applying CINEs to cameras and displays. And then I will introduce two of our recent works, two accelerators actually, in this direction. Then in this slide, I would like to share our vision. We believe that imaging display revolution is coming if we can apply high-quality CNNs at edge devices for generating high-resolution videos. It will be a complete upgrade from our today's old-fashioned devices. For example, for the traditional image restoration problems, we can have unprecedented quality. For example, for denoising, we can have much better quality. For super resolution, we can increase the resolution like this. And we have seen many of evidence from many publication results. And more than this, we can have unimaginable applications by using CNNs. For example, if you have a photo of your kid and you think he is not cute enough, okay, then you can convert this photo into Picasso style. This is so-called style transfer. And more than this, we can even have unseen upgrade scheme. It means that even you have your cell phone at your pocket for 1 year, and then the company finds a better training mechanism or a better training data set, they can upgrade the parameters and they can upgrade your cell phones. Even you have buy these devices about 2 years later. And this idea can be extended to any trainable algorithm like HDR or denoising. It means that the company can add new functions to your devices even you buy these devices maybe 3 years later if they provide the new parameters. And we may also see the design approach for these products may change. I would like to use this slide to share this idea. Let's see how the current design approach for these products. Before implementing this chip, the project manager needs to define the applications they want. And after defining these applications, they will form an algorithm team to develop the algorithms. And then they will form a design team to design the architecture and RTL coding. And then they will send this RTL code to chip implementation team. And in this old-fashioned design approach, we can only have limited features because these features need to be predefined before we develop the algorithms. And we can see we also have a long time to market because the algorithm, architecture, and chip implementation, they form a sequential process. But for CNN accelerators, we can have a new design approach. In this case, we can define the architecture first, the computing architecture first, and then we can let the algorithm team to train any kind of models that they want after you define this architecture. And the chip implementation team can also do their chip, do their APR in parallel with the model training. So in this case, we can have unlimited features because we can define the features when we train the model. We can also have a short time to market. So in this case, in my opinion, I think the computing architecture guides will be more important than they are today. Okay, even we have seen so many opportunities, but we do not see these kind of products at our pocket now, right? Because there are many challenges. And here I would like to use this baseline denoising network for an example. Suppose we use the traditional inference flow. It means that we inference the network layer by layer. For example, for these 4K input images, we will inference this layer first and save all of these features to the DRAM. And then we do the next layer and layer by layer. So in this case, we will require up to 100 to 31 gigabytes per second for DRAM bandwidth. And please remember that for our conventional mobile devices, the DRAM bandwidth limitation is only about 20 to 30 gigabytes per second. And for the computation demand, it will require up to 100 tera operation per second for this model at 4K resolution. So in this case, you either run out of your battery very soon, or you just burn your display. So we already see that we have challenges in huge DRAM bandwidth and intensive computing power. And now we can take a look into the reasons behind these challenges. It's because we need to generate high resolution images. So we need to generate high resolution feature maps, and they are high throughput and fine texture for local details, and they are also high precision for display. So combining these factors, we will expect that we will have a very high resolution feature maps, and the models are also not dense, are also not sparse. So these factors lead to our simple challenges factors: DRAM bandwidth and computing energy. Okay, now I would like to introduce our first related work, CINE processor, to see how we address these two challenges. And in this slide, I would like to introduce the background of this work. Previous work or previous accelerators only support a shallow, maybe just only at layer network, and only generate full HD resolution videos. And in this work, we would like to increase the depth to 21 to 29 layer. And we also raise the resolution from Full HD to 4K Ultra HD. So by using a deeper network, we can have a better visual quality as shown here. But because we increase the resolution and the depth together, we also raise the memory cost and the computing energy. So to address these two issues, we propose a memory efficient overlap stripe inference flow to reduce the memory cost, and also a highly parallel structure-sparse convolution engine to reduce computing energy. Okay, for the memory issue, to reduce DRAM bandwidth, a technique called layer fusion is widely adopted. It means that we do not inference the image layer by layer. Instead, we will first partition one image into several blocks. And then for each block, we will inference all the layers together. So in this case, we do not need to store these intermediate feature maps to the DRAM. But this technique has its own problem. It's because there are many overlap features between these blocks. So we need to figure out how to handle these overlapped features. For example, for this reference work, the authors proposed that we can reuse we can suppose we scanned these blocks in the horizontal direction, and this reference work they proposed we can reuse the overlap features here in the horizontal direction, and then we can save the vertically overlap features to the DRAM, and then take it back when we move to the next row. In this case, we will need a frame-sized external memory access because we stored these frame-sized vertically overlap features in DRAM. And in this reference work, the authors suggest that we can store these features in the on-chip SRAM to avoid the frame-sized external memory access, but it will induce a frame-sized SRAM buffer. You will need a quite huge SRAM buffer to store these vertically overlap features. And in this reference work, the authors, myself, okay, I said that maybe we can consider that we do not reuse these features. We can simply recompute them. We do not need to reuse them either in the SRAM or DRAM. We can just recompute them from scratch. Okay, so in this case, we can reduce the SRAM size and also the DRAM bandwidth, but we induce the recomputing overhead. So this is also not a very good solution. Okay, so for the CINE processor, we propose a new inference flow. So in this case, we propose that we can reuse the features in the horizontal direction, but for the vertically overlapped features, we can use the recompute strategy. And in this case, we can have a balanced solution in terms of SRAM size and external memory bandwidth compared the three previously mentioned works. Okay, let's move to the computation problem. And in here, we simply propose to apply a structure-sparse convolution. Here, we simply zero out some values in the convolutional kernels directly to facilitate the highly parallel convolution engine design. So here, we zero out these 4 values and when we move to the next channel, we zero out these 4 values. And because it is very regular, so we can have a better implementation for ASIC implementation. Okay, so in this diagram, we can see that we can use only a 44.4% of sparsity to have similar quality with the dense network. So we reduce about 2/3 complexity with the same image quality. And combining these techniques, we have fabricated the chip using a 40nm technology. And comparing to previous works, we can support more applications, including denoising and style transfer. We also raised the resolution from Full HD to 4K Ultra HD. And considering the external memory access, we also have a low number compared to these 2 works. We also built a complete chip demo system for this chip. And you are welcome to come to my lab. I will ask my students to prepare the demo for you. Okay? You can find yourself style transfer in real time. It's quite interesting. Okay? And now I would like to talk about our second work, VISTA. So far, when I talk about the CINE network, it means a single image network. It means that we only use one single image input to generate one single image output. But when we apply this kind of CINEs to generate videos, the temporal information between different frames is not leveraged in this kind of single image network. So the VISTA accelerator, for this accelerator, we aim to support video CNNs to leverage temporal information. And this is a basic structure for the video CNNs. It consists of 3 stages: extraction, alignment, and reconstruction. And first, we will have n input frames, and we will extract layer features separately. And then in the alignment stage, we will align them and fuse them into one single frame. And finally, we can use the reconstruction stage to generate the final output. And this slide shows that if we use multi-frame inputs, we can enhance image quality. For example, we can use the same model parameter size and have a higher PSNR numbers. And from this subjective view, we can also find that using video CNN, we can have sharper and clearer image. But when using video CNNs, we also increase memory bandwidth and complexity, in particular for the extraction part, because we have, for example, for the numbers here, we have 7 input frames, so we increase the complexity by a lot for the extraction part. Okay, so to reduce this problem, we propose a cuboid-based layer fusion technique. But let's first see what would happen if we directly extend the conventional layer fusion to video CNNs. Here we can see there are 3 axes. So for conventional layer fusion technique, we will inference one block and then go to the next block. So for each block, for example here B0, we will inference all of its related layers, extraction, alignment, and reconstruction first, and then we will move to next block. Okay? But in this case, when we finish all of the blocks for this time step T1, when we move to the next time step T2, we will find out that these 2 blocks, the features here, are recomputed because they already appeared here. So when we directly extend layer fusion technique to video CNNs, we will waste a lot of computation. And also we will waste some external memory access to reaccess these 2 input frames. So we propose to do the layer fusion in a cuboid-based way. It means that for this block, we will move to the time direction first. So in this case, we can reuse the feature maps generated here and also the input bandwidth here. And we can see that when the cuboid length, when it is longer, we can reuse more feature maps, but you will also need more SRAM to restore these features. And in this diagram, we can see that when we're using the cuboid-based layer fusion technique, we can reduce about 33 to 53% of EMA, external memory access. And for the computational complexity, we can also reduce by 19 to 42%. Okay, and now I would like to move to the computation complexity problem. And here the basic idea is that if we can use real number to construct neural network, why cannot we use complex numbers to construct neural networks? So consider that we can combine the two real numbers into one complex numbers. And for one complex number multiplication, usually we will need 4 real number multiplications, right? But there is a fast algorithm that can only use 3 real number multiplications for one complex number multiplications. So in this case, when we use complex numbers to construct neural network, we already save 25% of complexity. So following this line, we suggest that we can combine n real numbers into one new number. And then for this new number system, we can define an efficient multiplication operation. We can define a new multiplication operation to reduce the computation complexity. And this is our final finding. We find that we can reduce the complexity to only 25%, or in terms of area efficiency, we can have 4 times of area efficiency with only a graceful image quality degradation. And this is the detail of the adopted ring structure in CINE processor. Here, we combined 4 real numbers into one element, and then we perform, and for the multiplication, we can simply define the element-wise multiplication. So in this case, for a regular 4x4 matrix, we will need 16 multiplications, but in this case, we only need 4 multiplications. So we can reduce the complexity by 75%. But in this case, the information between these channels are not interchanged. So we designed a new directional ReLU to mix the information between these channels. It means that before this element-wise ReLU, we will perform Adama transform first to mix the information between these channels. And after the element-wise ReLU, we will perform the Adama transform again to convert back to its original domain. Okay, so combining these techniques, we fabricated the chip, also using 14 nanometer technology. And in this case, we can use only about 700 milliwatts to support 4K video applications. Okay, I know everyone is hungry, so I quickly move to my summary. And in this talk, I introduced that high-performance CNNs can enable next-generation cameras and displays if we can take care of these 2 challenges, DRAM bandwidth and computing energy. And I also showed 2 of our design examples to support this point. The first CINE processor can provide high-quality 4K applications using only 0.9 gigabytes per second of DRAM bandwidth. And the second VISTA processor, it can support high-quality video CNNs also for 4K Ultra HD displays when only consuming about 700 milliwatt of power and 3 gigabytes per second of DRAM bandwidth. I hope that I have shown you that the next generation cameras and displays are already around the corner for us. Thank you.
Thank you very much for the great talk. Do we have any questions? So, I'm not so much of a hardware expert, but I wonder, like at the end, you mentioned that when you convert to complex numbers, you're able to reduce like 25% complexity just by, for the multiplication itself, right? But I see that you have much more improvement. So by doing this, by converting to complex numbers. So where do those advantages come from?
Okay. Okay, for the complex number, we call it a field. It means that for complex number, we need to define the addition, multiplication, and also the division. But for CNN, I find that it seems that we do not need the definition of division. If we remove the definition of division, it becomes a ring. So we relax the constraint of division. So we can investigate so many different ring types to find out the best one, which can reduce the complexity and while also maintaining the image quality. Okay.
I see. Yeah. And how would you the complexity you're talking about here is for inference?
Yes.
Yeah.
For inference.
So how would you do the training? Would you do the training offline and then load the parameters inside the hardware, or can you just do it directly on the platform?
For this technique, we need to define the structure also using the ring structure. So we need to do the model training offline and apply this model. Yep.
Thank you. So, any other questions? So if not, let's thank Professor Huang again.
Thank you.